Hello students, let us continue with our discussion on countability of sets. So today we will be discussing the countability of the Cartesian product of the set of natural numbers with itself, that is the ordered pair of natural numbers n cross n. Okay, we will show that n cross n is countable. Next we will also prove one theorem which says that countable union of countable sets is countable. And we will also see some examples of sets which are equivalent to other sets, and the equivalence is quite interesting. Okay, for example, we will see that there are as many real numbers between 0 and 100 as there are real numbers between 0 and 1. Okay, so some interesting properties you will see, right? So let us have a look. The first theorem for today: the set n cross n is countable. That is, the set of ordered pair of natural numbers is countable set. Okay, so it is enough to construct. So by the last theorem that we had done, we had done a theorem which says that there are three equivalent criterion for countability of a set. First is, if a set is countable if it is finite or there exists a bijection between n and the set, the given set, right? And the second one was a set A is said to be countable if there exists a 1-1 map from A to n. Okay, and the other one was the set is said to be countable if there exists an onto map from n to A. Okay, so we can use any of these conditions because many a times it is very difficult to construct bijection. Okay, instead it is easier to construct only 1-1 map or only onto map. Okay, so let us see. So that is why we have started the proof this way. It is enough to construct a 1-1 map from n cross n to n. Okay, right? So we define a function f from n cross n to n as this: f of nm is 2 to the power n multiplied with 3 to the power n. Okay, for every nm belongs to natural number. So it's a well defined map. So 1-1 goes to what? 2 to the power 1 into 3 to the power 1, that is 6, right? 1-2 will go to 2 into 3 square, that is 18, like that. Okay, 2-1 will go to 2 square into 3. Okay, that way. So we show that this set is this function is 1-1. Okay, so let nm and pq belongs to n cross n such that their images are equal. Okay, so what we have to show? We have to show that the order pairs are equal. Nm is equal to pq. So f of nm equal to f of pq means what? 2 to the power n into 3 to the power m is equal to 2 to the power p into 3 to the power q. But one thing is to observe is that these are all natural numbers. Okay, 2 to the power n into 3 to the power m, this is a natural number. 2 to the power p into 3 to the power q, this is also a natural number. Okay, also you observe that 2 and 3 are prime numbers. So this is nothing but the prime factorization of the particular natural number. Okay, the LHS is also the prime factorization of the same natural number. Okay, and we have a fundamental theorem of arithmetic which says that any given natural number can be factorized or expressed as a product of primes in a unique way. Okay, right? So that is what we will write. So 2 to the power n into 3 to the power m and 2 to the power p into 3 to the power q are the canonical forms of the same natural number. Okay, because of the equality. But by fundamental theorem of arithmetic, the canonical expression is unique. Okay, suppose 12 can be factorized only as 2 square into 3 and not in any other way. Okay, as a product of primes, right? So by fundamental theorem of arithmetic, the canonical expression is unique. Hence, n should be equal to p, m should be equal to q. Okay, so f is 1. So we have proved that n by n is n cross n is a countable set. The set of ordered pair of natural numbers is countable. Okay, so we can have a look at another visualization of this n cross n using a graphical plot, which will also help us to understand that how there is a bijection between n and n by n. Okay, I have done the proof with only 1-1 map, but observe that the map that I had given you here, it is not onto. Okay, so this is not a bijection. This is not a bijection. It is just a 1-1 map from n cross n to n. But we already have the equivalent criteria. If there exists a 1-1 map from the set to the set of natural numbers, then the set is a countable set. Okay. So let us have a look at this graphical arrangement. In this case, we can construct a bijection. Okay. Of course, we can construct it rigorously, but here just let us have a look at this, how this is constructed. Okay. So you consider this as the, so there are two axes. It's like x-axis that we call, it's like y-axis, except the fact that it starts from 1 here. So the ordered pair 1-1 is written here, ordered pair 2-1 is written here, then 3-1, 4-1, everything with the second coordinate 1, okay, is written along this axis, right? Everything with the second coordinate as 2 is written as written along this axis. Okay, everything with second coordinate 3 is written along this. Okay, like that. So you draw lines passing through 1, n and n, 1 for each n. Okay, so we keep on drawing lines. Then you will see we have actually constructed a bijection. Say this is the 1-1 is the first element, 1-2 is the second element. Okay, then say 2-1 is the third element. Okay, like that. This is the fourth element, this is the fifth element. Okay, f of 5, this is the sixth element. That way we can construct a bijection. Okay, so that is how n cross n is countable. So we have a bijection of this type. Okay, we can also write a explicit expression for this. It is there in the real analysis book by Bartel and Sherbert. You can have a look. Okay. Next, let us have a look at this. If you are given two countable sets, then their union is countable. Okay, so union of two countable sets is countable. So let A and B be two countable sets. If A is phi, that is empty, then A union B is what? It is B. So B is already given to be countable. If B is phi, then A union B is A, which is also countable. So let us start with non-empty sets. So let A not equal to phi and B not equal to phi. Then A and B can be written as what? In the last class I had already remarked that any countable set can be written in this way: A1, A2, A3. This B is also countable, so we can write it as B1, B2, B3 like that. Okay, but there is an important thing you have to note here, that A and B may be finite sets also. Okay, in that case the list will not continue indefinitely. But since we are using a common notation for finite as well as infinite, so we adopt some convention here. We adopt the convention that if it is a finite set, then the last element that is listed is actually repeated. Okay, repeated, that is an equal to a mod a. Mod a is the number of elements of a for every n greater than or equal to mod a if a is finite set. Okay, if a is finite, then say a has 10 elements, then A10, A11, A12, everything will be same as A10. Okay, we will take that. This is just for notational convenience. Okay, otherwise we have to do it separately for this finite and infinite case. Okay, so it's not necessary. So that is why we adopt this convention. Okay, this will help us. Okay, Bn is equal to B mod B for every n greater than or equal to mod B. Mod B means the cardinality of B, that is the number of elements of B. Okay, so here I have written mod A means the number of elements of A. Similarly, mod B means the number of elements of B. So we define f from A to n to A union B as f of n equal to A, f of n equal to A, n plus 1 by 2 if n is odd, and B n by 2 if n is even. Okay, and we show that f is an onto map because it is enough to construct an onto map from n to A. Okay, to show that A is a countable set, it is enough to construct an onto map from n to A. Okay, that is what we are doing now. So n goes to A n plus 1 by 2 if n is odd, and it goes to B n by 2 if n is even. Okay, so we show that it is onto. So for that we take any element from the union. So let y belongs to A union B be any element, then y is equal to am for some m belongs to n, or y is equal to bm for some m belongs to n. Okay, because an element inside A union B is either in A or in B. If it is in A, it can be written as AM. If it is in B, it can be written as BM. Okay, for some M. So if y equal to AM for some M, then we already have twice M minus 1 is belongs to a natural number which is odd. Okay, and f of twice M minus 1, by definition it will be A twice M minus 1 plus 1 by 2. Okay, so that is nothing but AM. Okay, so we can have a rough calculation here. We need to find out the value of n for which n plus 1 by 2 is equal to m. Okay, so that n should be twice n minus 1, twice m minus 1. Okay, so if y equal to bm for some m, then bm corresponds to even numbers. So twice m is even. If m is a natural number, twice m is even, and f of twice m can be written as b twice m by 2. Okay, which is equal to y. Right. Thus, every element in A union B has a pre-image in N. So F is onto. Therefore, A union B is a countable set. Okay. So this is proved for two sets. So union of any finite number of countable sets is countable. In fact, this next result that we are doing, it shows that countable union of countable sets is countable. Okay. So you take any collection of any countable connection of countable sets, then it is their union is countable. Okay, so if AM is a countable set for each M, that means these indices are coming from a subset of the set of natural numbers. Okay, such a collection is said to be a countable collection. Okay, if the indices that we are using AM, okay, they come from a set, they come from a subset of the set of natural numbers. Okay, then the collection is said to be a countable collection. Okay. So a countable union of countable sets is countable. That is what we have to prove. Okay. So the intuition is almost the same that we had seen. This countable collection, say A1, the elements can be written as A11, A12, A13, A4, like that in matrix notation. Okay. A2, for the set A2, the elements can be written as A21, A22, A23, A24, like that. Okay. For A3, they can be written as A31, 32, 34. So these are very much similar to the ordered pair of natural numbers, nothing else. Okay, see 31, 22, 13. These are just ordered pair of natural numbers. So n cross n will come to our rescue. Okay, we can use n cross n to prove this theorem. Okay, so since AM is countable for each m belongs to natural number, so there exists onto function fm from n to am for each m. Okay, for each m we will get an onto function, right, because we already have the equivalent criterion for countability. So we define one function phi from n cross n to union of this as phi of mn is fm of n. Okay, this is the image of fm under n. Okay, it is the image of n under fm. Okay, like that. So we show that phi is onto map. Okay, so how to show that it is onto? Let us start with an element in the union, then y belongs to am for some m, right, but already fm from n to am is onto. This is already onto. Okay, so there exists an element n inside natural number such that fm of n is y. Okay, so y is nothing but phi of mn, so phi is onto. So we have shown that phi from n cross n to the union of the countable union is onto. Okay, but I have to construct a onto map from n to the union. Okay, so but already we have shown that n cross n is countable. So n cross n is countable means there exists an onto map from n to n cross n. Okay, you take the composite of this to onto map, phi composite with psi. Okay, so that is also onto. Composite of two onto functions is onto. Okay, so these were done in the first semester. So thus phi composite with psi is from n to this union is also onto. So hence this is a countable set. Okay, so we have shown that countable union of countable sets is countable. Okay, now next there are some interesting results. We will see later that these sets that we are considering now, this is intervals, they are not countable. Okay, we will see that in the very next lecture. Okay, so the interval 0 1 contains much more elements than the set of natural numbers itself. Okay, show that the intervals 0 1 and 0 100 are equivalent. That means there exists a bijection between 0 1 and 0 100. That means there are as many real numbers between 0 and 100 as there are real numbers between 0 and 1. Okay, the number of real numbers between 0 and 100 is not more than the number of real numbers between 0 and 1. They have the same number of real numbers between them. Okay, it's quite surprising, hard to digest, but you will see once we construct the bijection, it is very clear. We need to construct a bijection from 0 1 to 0 100. So you can take this bijection f from 0 1 to 0 100 is defined as fx equal to 100x. Okay, f of x is equal to 100x. So we have 0 less than x less than, so let us see whether this 100x is an element inside the codomain or not. So for every element in the domain, 0 less than x is less than 1, and so you multiply all sides by 100, so you will get 0 less than 100x less than 100. That means 100x lies in the interval 0 to 100. So f is well defined. Okay, so and f is 1 1, it's very simple to prove. F is 1 1, 100x equal to 100y implies x equal to y. Then you can prove it is 1 on 2. You take an element inside the codomain, then that element lies between 0 and 100, divide both sides by 100, so you will get y by 100 lies between 0 and 1. Okay, so you take that y by 100 as x, so f of x is equal to y. So every element has a pre-image, so f is a bijection. So 0 1 and 0 100 are equivalent. This means that there are as many real numbers between 0 and 100 as there are between 0 and 1. Surprising. Okay, isn't it surprising? Quite surprising. There are as many real numbers between 0 and 100 as there are real numbers between 0 and 1. Okay, so there are some more examples where also you will see any closed interval, say 0 1 is equivalent to any other closed interval AB. Okay, closed interval 0 1 is equivalent to any other closed interval, whatever closed interval you take, however large it is. Okay, so you see how to construct this function. We construct a function from 0 1 to AB as f of x is a plus b minus a times of x. Okay, right. So in this case you will see that this function is actually bijection from 0 1 to AB. Okay, so it's your exercise. I have given you it as an exercise. You can easily show it's a bijection, so you try it yourself to show that it's a bijection. Okay, next you can also show that 0 1 is equivalent to 1 infinity. There are as many real numbers between 0 and 1 as there are real numbers greater than 1. Okay, number of real numbers greater than 1 is same as the number of real numbers lying between 0 and 1. Okay, very surprising results. It's very hard to believe, right? There are as many real numbers between 0 and 1 as there are real numbers greater than 1. Okay, but once you see this graph, it is very clear. Okay, the graph of y equal to 1 by x from 0 to 1. Okay, so for each point here there is a point here, right? For each point here there is a point here, right? And as you go close to 0, the value of 1 by x keeps on increasing. Okay, even then there are some values, right? For each x inside 0 and 1, you will get an x 1 by x in the set of real numbers. Okay, so this function defined by fx equal to 1 by x, where x belongs to 0 1, it's a bijection. Okay, it's very easy to show it's a bijection. So this also I have given you as a homework. You try it yourself. Then you show that the open interval minus pi by 2 to pi by 2 is equivalent to r, the entire r. There are as many real numbers in the world as there are real numbers between minus pi by 2 and pi by 2. Okay, every real number corresponds to a real number between minus pi by 2 and pi by 2. Okay, so for that we can just have a look at the graph of fx equal to 10x. Okay, as x tends to pi by 2 plus pi by 2 minus, the graph of 10x or 10x tends to plus infinity. Okay, and as x tends to minus pi by 2 plus, fx tends to minus infinity. Okay, so the graph of fx covers the entire the range, you can see the range of this 10x is the entire real numbers. Okay, so f is a bijection, so from the graph it follows, right? So and show that any closed interval AB is equivalent to any other closed interval CD. Okay, so this is also true. Any closed interval is equivalent to any other closed interval. So we observed that x belongs to AB implies x lies between A and B. So x minus A lies between 0 and 1. Okay, we will try to relate this with 0 and 1. Once we get that it lies between 0 and 1, if you multiply this by the length of the second interval, then 0 less than or equal to d minus c into x minus a by b minus a less than or equal to d minus c. Okay, and then you add c to all sides. So this particular quantity, it lies between c and d. Okay, and you can show that if I define the function this way, fx equal to c plus d minus c by b minus a into x minus a, then it is a bijection. Okay, so there are as many real numbers between AB as there are real numbers between C and D. So say closed interval 0 1 is also equivalent to closed interval minus 5000 to plus 5000. Okay, like that. So these are quite interesting results when we consider infinite sets. Okay, so in the very next lecture I will discuss that these sets are actually uncountable. Okay, 0 1, open interval 0 1 is uncountable, right? And we already have a result that every subset of a countable set is countable. Okay, what is the contrapositive? Every superset of a uncountable set is uncountable. Okay, right? If you have if A is a uncountable set and A is a subset of B, then B has to be uncountable, because if B is countable, then every subset has to be countable, right? So that is not possible. So B has to be uncountable. Every superset of an uncountable set is uncountable. Okay, that so we will show that 0 1 is actually uncountable, and from there it will follow that the set of real numbers is uncountable. Okay, so that will be probably the last result of our course, right? This first unit, sorry, not the entire course, the first unit. Okay, so please try to do these problems yourself. So in the next lecture we will discuss. Thank you.